Hello and welcome to another video where we are going to practice some of the typical problems you can see in this topic. We're still in topic 4 where we are introducing basic statistical inference, hypothesis testing, and the idea behind that. I've broken that up into 3 parts. This is the third part, and the B indicates that part A was our lecture, that's done. B is where we just walk through a problem from start to finish. And the book we are using is my favorite statistics book for an introduction, regardless of your discipline. We're going to go to page 173 and to number 18. Just going to move this around so we can see it like so. So let's have a read through here first and see what we are working with. And of course, this follows from the lecture, which I assume you understand first, and then we're just taking these problems to solidify the concepts that were introduced. For each of the following studies, the samples were given an experimental treatment and the researchers compared their results to the general population. For each, carry out a z-test using the 5 steps of hypothesis testing. For a two-tailed test at the 1% level, make a drawing of the distributions involved, figure the 99% confidence interval, but one thing at a time. We'll focus just on A and slowly walk through the steps. Number 18 here. A. So we have two populations. Population 1 is, let's say, the individuals that we are investigating. Individuals under investigation, of which we have a sample. And population 2 is the general public. Depends on the question, of course. This is just sort of a short version of a more detailed word problem. Let's say in general here. So I don't know, is it the rest of the country that I'm comparing it to or what? I'm giving people a treatment and then I'm taking a sample of that, of course. So our null hypothesis is that our population 1 is the same as in general, which is given as 10. Standard deviation is 2, we could use that. And we have a sample of 50 from population 1. And our research hypothesis is then, because it's a two-tailed test, that the population mean is not 10. Now that's secretly perhaps what we're hoping for, and under the assumption of the null hypothesis, then we investigate the evidence and see what it suggests. So let's go ahead and do that. So I'll number these to match the book, the steps of hypothesis testing, just to give me some structure in walking through the thought process. So step 2 is where I look at the comparison distribution. Comparison distribution is going to be the distribution of means. Even though I'm investigating the population of individuals, the sample is what I'm working with, and I'm comparing all possible, or I'm thinking of all possible samples of that size that I could get. So my sample mean is going to be the same as the population mean, or sorry, the mean for the distribution of means is the same as that for the individuals, but my standard deviation for the distribution of means, I'll refer you to our formula sheet over here. This one in 5-2 gives the variance, even though we want the standard deviation, but that's a simple fix. The variance of the distribution of means is the variance of the population of individuals divided by the sample size. So then if I want the standard deviation, I just square root that. So I'll write it like this over the square root of the sample size. And in our case, the standard deviation is given as 2, and our sample size is 50. So let's calculate that. Go to my calculator here in the Discord chat, and I'll calculate 2 divided by square root of 50. Of course, you can use your own calculator. We get there. What do we get? 0.28 if I round it. All right, so this is our comparison distribution. When did they say we should sketch it? Doesn't really say. Make a drawing of the distributions. Okay, so we could do that now or later. Why not squeeze it in here? All right, so my comparison distribution, I'll do it over here. I have space over here. Why not? Let's put it over there. It's centered at the same mean under the null hypothesis, which will be here at 10 or a 0 z-score, whichever one you want to write down. Little thinner, faster drop down because my variance is much smaller in the distribution of means versus the distribution of the individual scores. So now I want to know what is my cutoff score using, what did they say, alpha of 1%, I believe. 1%. Z-test, 5, two-tail test, 1%. Okay. Two-tail test, you can see that here as well. Alpha is 1%. Decimal is, of course, 0.01. I'll remind myself here that it is a two-tail test, but it fits with the setup of the hypotheses. So that means if I visualize that over here on my comparison distribution, I'm going to have my Z cutoff plus or minus Z cutoff. Let's write a minus and a plus like that. So that 1% combined in the tail. So this will be 0.5%. 0.5%. Decimal equivalent will be half of this. So I'll have 0.005, of course. And then in here, I will have 99% of the scores. So then I go to my table and I'm looking for the tail, 0.5% in the tail. It's pretty small, but that's what they want, 0.5%. So I'm looking at the right column for the tail. I almost never look at the left one here. The tail is, I can always convert it to the tail if I need to. I'm looking for 0.5%. Ooh, that is small. 0.5%, 0.5%, almost there. And again, unfortunately, because the book just has a summarized table, my 0.5 sits in between those. Different people do different things, like I've said before. One option is to average out these two, which is what we'll do. So halfway between these, 2.575. So my Z cutoff score I'll do it like this. What did I say? 2.575. Yes. Some people take the more conservative of these two. If you're using software, there's no issue because you'll have all the gaps filled in. So it's really when we're doing it by hand. And then that's not what I would do for a proper research project anyway. So it's not really a big deal. The thought process is the same. All right, so we could write that in here, 2.575. And next, we want to see, well, what is our observed score in terms of z-scores? Everything is standardized. Well, what did we observe? Let's look at the question. In the question, we took a sample of 50 and we observed a sample mean of 12. So in that distribution, observed score minus comparison distribution mean over comparison distribution standard deviation is how we standardize it. So let's write maybe our mean was, I just said it. What was it? 12. 12. Our population mean for the comparison distribution we have up here was 10. I'm just copying it. And the standard deviation for the comparison distribution is 0.28. Yes, I know I've rounded that. And in general, when you do things properly, you shouldn't use a rounded number in a future calculation. But when we do it by hand, we'll let that go just for the sake of convenience. But if I want to be as accurate as possible, then we should always use the most accurate values that we get until it's the very final answer. So our z observed is going to be, see, do we have a formula for that in our formula sheet? Not really, because it's very similar to 3.1 that I can just sort of use that to remind myself how to standardize something. Yes, so don't be too confused if you don't see it exactly like this. I'm just writing out all the detail to practice for any future clarifications if it's needed. So let's see what we get there. We'll put that in to our calculator. 12 minus 10, just to be thorough, 0.28. And we get 7.14. So we're comparing our cutoff to our observed score. Did I do that right? 12 minus 10 over 0.28. Okay. So our observed score is z observed much, much greater than, in this case, the right cutoff. So under the assumption, or let's say it like this, if I assume that the null hypothesis is true, then 99% of sample scores, sample means, observed scores, will fall within these cutoffs. 99% of the time, I'll just get that. Now I get something outside of that. We consider that to be so extreme and so rare that it's not just going to happen by accident. And it suggests that the distribution actually is not over here, but maybe more sitting at a place where a 7.14 is considered a fairly common observed score to get. And we consider the evidence therefore strong enough to suggest that the null hypothesis is not what's happening here. But in fact, the true population mean is different. Okay, so that's how the reasoning behind our eventual conclusion, which is number 5, conclusion. Now you can phrase this in many ways. I'll say here, since the observed z-score is greater than, in this case, the positive cutoff z-score, could have been either side, we reject the null hypothesis in favor of the research hypothesis and conclude that the evidence is strong enough. That's why we have a cutoff to know when is it strong enough. When is our observed, when is rare and extreme enough? That's the whole point of the cutoff. The evidence is strong enough to suggest that the true population 1 mean is different from, I guess, population 2. In other words, the treatment, whatever it was, experimental treatment, the evidence suggests that it does make a difference. Just note that, yeah, never mind. We can phrase this in general with our populations, or add another sentence and say the evidence is strong enough to suggest that the experimental treatment has an effect and does in fact change the whatever property we're measuring. They don't really say. Lastly, we want to just add another part at the end for practice sake, where we want to calculate our 99% confidence interval. And of course, do I have space? I do have some space. Here, this of course continues from the lecture that we did in the A video, 4.3a, where we introduce the idea here. Now, confidence interval can be interpreted in a variety of ways, and some people get a little obsessed with the perfect technical interpretation of it. I think that's slightly missing the point at an introductory level, which is where we are. So remember that we've now concluded that the evidence suggests that the mean is somewhere else. We don't know what it is. Our best guess for the mean is our sample mean of 12. So if I just sort of briefly visualize this on the new graph, just for convenience to not have the other one be too messy. Over here, our best guess is now to center it around our mean of, was it 12? I think it was 12. 12. And to say that, well, we don't think it's the what was it, 10? We don't think it's 10. We don't know exactly what it is. We think it's closer to 12, but of course we're not sure. Let's just give ourselves a little window here to play it safe. We can't say with confidence that it is 12. We don't know, because our sample, even though the true population mean might not be 10, when we take a sample, we're going to get some random fluctuations above or below the mean. So we can't say that it's 12. So we spread our net a little bit wider using a confidence interval that we choose, and we chose the 1% or 99%. So this matches the confidence level of the hypothesis test. We chose an alpha of 1%, so the confidence interval will be constructed as a 99% confidence interval as well. So we're going to use the same idea of a 0.5% in the tail. We're now just building it around this best guess for where the center of the distribution is. And then our z-score that gives us 5% in the tail is the same as what we did previously. 5%. Oh, sorry, 0.5% in the tail. 2.575. So z-score here, 2.575, and this will be a negative 2.575 z-score, of course. And then we build our interval. The left side will be the mean of 12 minus the z-score that we got with the positive, the absolute value of the z-score times the sample, sorry, not the sample, the standard deviation of that distribution, because we assume that the variance is the same throughout, and then plus on the other side, like so. And what we get on this side, let's write it out. It is our 12 minus 2.575 times standard deviation was 0.28, wasn't it? Pretty sure. And this one will then be 12 minus 2.575 times 0.28. Of course, we've rounded to 8 as the 0.28 as well. So some inaccuracies due to rounding, but for a rough hand calculation, I'm okay with that. As we continue and we incorporate software more and more, we'll see that we can be more accurate with the aid of these tools. So let's do the left one. 12 minus 2.575 times 0.28. And we get 11.28. I'll round it again. And then the other side, 12. Oh, I wrote a minus again. No. That should be, of course, a plus. Back to my calculator. To plus 12 plus 2.575 times 0.28. And we get a 12.72, let's say. So that is going to be our confidence interval. 99% confidence interval. Now a variety of ways that you can phrase your interpretation of this interval, some more casual than others. I guess the first and technically most correct interpretation is that overall the samples that we could get, and therefore all these confidence intervals that we could get, because they're centered on our sample. You do this whole thing again, you might not get 12 as your sample mean, right? You might get 11.8. You might get a 13. I don't know, it depends on the variance. You're going to get some fluctuation. Out of all the samples and therefore confidence intervals, 99% of them will contain the mean. A more, let's write that down. Interpretation. It's always nice to have something written down. Say here 99% of all possible confidence intervals will contain the true population mean. There we go. Now, in a more casual, slightly less technical interpretation that at this level I'm okay with, you could say that there's a 99% probability that this confidence interval or that this interval contains the true population mean. Now, a little disclaimer, I understand that some people get all up in arms that technically you could argue that's not quite correct based on the formal definition of probability, but at this introductory level, I'm perfectly okay if you interpret it that way as well, because it fits with our basic intuitive understanding of the word probability. All right, so let's review very quickly our 5 steps in hypothesis testing. Even though the situation in the future might get more complicated, these 5 steps don't really change. So it's a nice template to work with. We have our setup, population of people that we're investigating versus something in general, and our hypothesis, in this case a two-tailed test that we're setting up. Then we look at our comparison distribution, and because we have a sample that we're working with, we're trying to see how that sample sits in comparison to all possible samples we could get, and therefore we're looking at the distribution of sample means, and we make the adjustment to the standard deviation. Then we look at where our observed, oh sorry, no, that's 4. Number 3 is we then decide on our confidence level and the cutoff appropriately, two-tailed in this case. We then see where our observed score, our observed sample mean, puts us by standardizing that to an observed z-score, and then comparing that to the cutoff z-scores. We can then make a decision in terms of how extreme do we consider this observation to be if the null hypothesis is actually true. If it's very extreme, it's very unlikely that we would just randomly get this. If the null hypothesis is true, it suggests that the null hypothesis is actually not true and the distribution is actually positioned not at the 10 we assumed. Then an alternative approach, we then say that alternative approach, which essentially does the same as hypothesis testing, your conclusions will match because you're using the same confidence level, is to construct an interval around our observed sample mean in an attempt to quote unquote capture the true population mean, in an attempt to have an interval. We don't know exactly where it is, but within normal fluctuations, we're trying to get an interval where it should sit somewhere in there. It could be right next to 12.72. Could be right in the middle. We don't know for sure. The interval is sort of a way of hedging our bets that we can't say exactly what it is. We can just say it's somewhere in this range with a certain degree of confidence. All right. Hopefully that gives you a better understanding of all of this. This was the last topic the last part of topic 4, where we did an example by hand. We'll follow that up by doing another example, but with the aid and convenience of a spreadsheet, and then we'll move on to the next topic. All right, until next time.